we are faced with one of the simplest looking, yet deepest questions in the universe. Why does time always flow forward for us? Think about it. A cup of tea cools down, but it never heats itself up. A shattered glass does not reassemble itself. We grow older, but never younger. Time flows in one direction, irreversible. Yet, the laws of physics, especially at the quantum level, show no preference for time moving forward or backward. All quantum equations are time-symmetric, whether you apply time forward or in reverse. The equations always yield correct results. Hilbert's sixth problem, which has remained unsolved for 125 years, goes right to the heart of this mystery. And recently, a new mathematical study may have begun to lift the veil on this paradox. Let's clarify. What this paper claims to do is something that had not been done before, to mathematically prove that the arrow of time always points forward. As science enthusiasts, we may not possess the advanced mathematical knowledge required to fully grasp the paper, but we will try to concretely interpret what it says and decide together whether this proof is convincing. For that, we need to go back to the year 1900. David Hilbert was a German mathematician who lived at the turn of the 19th and 20th centuries. In the year 1900, at the International Congress of Mathematicians held in Paris, he presented a list of 23 major mathematical problems, the most important challenges he believed would shape the next century of mathematics. Hilbert's sixth problem asks a profound question. How can we explain complex systems in nature, such as a random movement of millions of gas molecules in a room, using simple, predictable rules? Take airflow, water currents, or the pressure of air around a flying plane. These are all made up of countless molecules constantly colliding with each other. Yet we can describe these systems smoothly and elegantly using the equations of fluid dynamics. They appear perfectly orderly to us. And that's exactly what Hilbert was asking. Can we build a solid mathematical bridge between the microscopic laws that govern individual molecular behavior and the macroscopic laws that describe the entire system in broad strokes? In other words, how does chaos at the small scale turn into irreversible, one-directional order at the large scale? This is precisely why the authors of the paper claim to have proven why the arrow of time always points forward, at least for beings like us, who exist at the macroscopic level. The idea is simple but powerful. Microscopic chaos does not just become order, it enters a one-way, irreversible flow of time. And in fact, that's what Hilbert's sixth problem is deeply connected to. So, how did physicists begin to tackle such a colossal question? The first step was to focus on the Boltzmann equation, which describes the motion of gas molecules over time. This equation treats the collisions and movements of millions of molecules statistically. In other words, instead of tracking each molecule, it asks, what does the system do as a whole? Imagine a stadium full of people. Rather than observing every individual steps, we focus on the overall direction in which the crowd moves. Each person may walk at a different speed or angle, but together, the crowd moves in a certain direction. The Boltzmann equation tries to capture this big picture, but writing the equation isn't enough. The real challenge is showing how this complex equation gives rise to the kinds of smooth airflow and patterns we see in everyday life. That's why the authors studied the Boltzmann equation under precise boundary conditions. They carefully defined the initial positions and velocities of the molecules, as well as the limits of the surrounding environment. Think of it like the stadium analogy again. It's not just about where people are going, but also where the exits are, what obstacles are on the field, and how the layout of the stands affects movement. These boundary conditions are the physical rules that determine where and how the crowd can move. Likewise, the scientists define a physical field that molecules move through with precision to understand the system's behavior at every level. After defining the boundary conditions, scientists moved on to the second stage, step-by-step calculations of how this molecular system evolves over time. That is, how it develops and changes. With the help of the Boltzmann equation, it was now possible not only to describe the initial distribution, but also to make concrete predictions about the system's likely direction of evolution over time. Let's think of this using the stadium example. When the gates open, people begin to flow in certain directions. At first, the crowd is disorganized, but over time, most people find the optimal exit and move toward it. Chaos gradually transforms into an organized flow. Similarly, the authors mathematically analyzed the behavior of molecules as it unfolded over time. They didn't observe the system at just one moment, but throughout its entire temporal evolution. And here, they noticed something very important. This evolution was always one way. Molecular clusters never spontaneously returned to their earlier disorganized states. the system consistently moved toward a more orderly and predictable structure. In essence, a process that began with time-symmetric laws would, after reaching a certain mass density threshold, lose its time symmetry, mathematically speaking. The paper's reference to the system moving toward order may sound like a contradiction to the second law of thermodynamics, but in fact, the two are entirely compatible because the order discussed here refers to macroscopic behaviors observed at our everyday scale. In other words, events like air currents, ocean waves, or water flowing through a pipe, which seem predictable and structured, are, at the microscopic level, the result of vast chaotic molecular motion. According to the paper, this tendency toward macroscopic order over time corresponds to Boltzmann equations gradually transforming into the equations of fluid dynamics. In this transition, the increase in entropy indicates that the system becomes more probabilistically disordered at the microscopic level. However, this disorder organizes itself in such a way that, when viewed from a larger scale, it forms recognizable patterns, such as flow behavior. From this point onward, the main goal becomes clear: to demonstrate whether the macroscopic equations of fluid dynamics, as we observe them, naturally emerge as a result of this microscopic evolution. This is, in fact, the of the paper. At this stage, the authors closely examine how molecular density functions change over time, and more specifically, how this evolution relates to entropy, and they arrived at a striking conclusion. The evolution of the system always proceeds alongside an increase in entropy. In other words, the system moves not from microscopic disorder to macroscopic order, but rather toward greater disorder. However, this growing disorder gives rise to behaviors that appear orderly on a large scale. And here lies a critical distinction. The order we perceive is an illusion of scale. In reality, the system's entropy is still increasing. To visualize this, imagine a stadium full of people, each moving randomly on their own. Now start a wave. People stand and sit in sequence, creating a beautifully organized pattern across the stands. Each person may still be acting individually, even chaotically, yet the collective result is visually structured. Similarly in physics, while entropy increases, what we observe externally is a smooth and organized flow. At this point, the authors clearly demonstrate that the increase in entropy aligns precisely with the arrow of time. That is, the fundamental reason why time only moves forward lies hidden in these microscopic collisions and the unstoppable growth of entropy. So, what do we learn from all of this? That the forward flow of time is not just a matter of perception. It's rooted in a simple yet profound truth. Entropy always increases. Even as molecules behave in chaotic, unpredictable ways on a microscopic level, we witness emergent order, just like the synchronized wave emerging from scattered people in a stadium. This paper, for the first time, shows step by step how this microscopic disorder mathematically gives rise to the orderly rules of fluid dynamics. And most importantly, it reveals this. What we call the arrow of time is actually a direct mathematical consequence of irreversible entropy increase. The importance of this paper goes beyond solving a century-old mathematical problem. It redefines how we understand the very fabric of nature. For the first time, the authors establish a complete mathematical bridge between the random molecular chaos and the structured, large-scale behaviors of fluid dynamics. And that bridge offers one of the most concrete explanations we've ever had for why time moves only forward. In other words, the arrow of time is not just an intuitive concept. It is a mathematical result of how molecular chaos transforms into irreversible physical order. The famous question Hilbert asked in 1900, how can a microscopic and macroscopic world be united, is finally beginning to receive a meaningful answer. Today, we've brought you a paper full of advanced mathematics. But the mathematical proof of why time's arrow always moves forward is a remarkable development for science lovers everywhere. Time may not be just a product of our perception after all. So in summary, time, which is merely a parameter at the microscopic level, gains a direction of flow as it scales up into the macroscopic world. If you enjoyed this video, found it thought-provoking or inspiring, please like, share, and consider supporting our channel. Let's reach even more curious minds together. See you in the next video. Take care.